Yeah, I was done pretty early with everything else, but that one I thought about it and I was reading the book for a while but I feel good about everything else. So, oh, we said hi, Sarah. Um,
Hi. Class. I heard that Stephen Hawking died the night before my midterm, and I ended up doing okay. That is an indication of
yeah,
anything. You don't need to worry.
I believe it's a time of transition between having been an undergraduate and having been becoming an independent scientist.
So I see that we're about to head into group theory territory.
Yeah, all the today. We have done it all along very secretly, but now it's going to become explicit. Theme is of the course is the symmetries are amazingly powerful, and mostly, you know, the way they teach you, let's say, quantum mechanics, it's all assumed the
Mhm.
symmetries are there, so you don't see the workings underneath the carriage. It's real engine that drives formulation of everything. We must carry on because I have lots of amazing stuff for today, even though this is just humble Fourier representations. Number one, finite number of point series, infinite number of points on a circle. And now we'll do transforms, which is continuum on a line rather than on a circle. An idea of Fourier series was we had compact support, we had a Bunsen burner, and we're doing better and better measurements on the height of the flame front or velocity of flame front. Somebody does it on 17 points, a better person does it at 213 points. So how are you going to compare all this in results? Only sensible thing is assume that there is a continuum limit. Continuum line, even though it's imaginary because we cannot specify any number to infinite precision, is a powerful way of going to the marketplace of ideas called physical review letters and buy and trade ideas in a way that we can all agree. So we go to continuum. Maybe it exists, maybe the nature is not continuum, but it's a very convenient way, very powerful way for us to share results. What happened, we traded in our Fourier series, which used to have 2m plus 1 points in it. We have taken m to infinity, which means in every open interval, right now we have points, they're infinitely dense. In that limit, we don't count the integer distance from the origin in increments of spacing, but we do it by continuous variable x, which runs around, and perimeter of the circle is either L or 2 pi, depending where you decide to describe it by perimeter, which is length, inches or something, or by a sensible thing, which would be just the angle, a dimensionless object. So that made sense, but now the inverse got to be weird. And now we have lost this beautiful symmetry for Fourier representations. The vector or its dual in a Fourier space was basically the same thing. There was just a plus or minus I sign in transformation. Transformation was unitary. But now we have this weird thing that the expression in terms of Fourier modes, and what does that expression mean? It means that we have a constant term, and then what we do is we add little wiggles onto this circle so that there is a constant term, but then there is a single wiggle where I go a little bit above. There is 1 humps, then there are 2 humps, then there are 3 humps, and each one of them has some strength. So people tend to think of this as listening to a modulation of air pressure or voice. and decomposing it into some of the frequencies. And those things have to be integers because they have to nicely, analytically, smoothly be continuous around the circle. So that, that's the meaning of the Fourier series. And if you write them in terms of sines and cosines, then, it's really familiar looking thing. But the inverse says that I take one of these integers, so I take one of these frequencies, and then I compute how strong is the component of my measured function, measured waveform on this interval. And, the symmetry is gone. It used to be beautiful symmetric. So that means you really have to continue this because, why did we decide that L perimeter of this circle is finite? It's true in one subset of physics called crystals, or one subset of art called periodic tilings or mosques in 2 dimensions, 3 dimensions, etc. But usually we also assume that when we sit at this point here, the end of the world is so far that I can assume the world is flat. And that's the assumption that's called the last version of our Fourier series. It's called Fourier integral. Transform is called integral because we'll make both of these things integrals, not one discrete sum, one integral. We started with discrete series, so infinitely many terms in a sum, where X is running on the perimeter of periodic domain, or is a finite segment of infinite line going from minus L to plus L. AM was minus L over 2 f of x e to the 2 pi I m. And now you say, in my laboratory, I'm measuring things in centimeters. I'm assuming that I'm on a grand circle on the Earth with this perimeter, but that's a very large number compared to, it's 40,000 kilometers compared to my centimeters. So let me take it to infinity. If I define a wave number to be m over L, L is now dimension full length. If I make this L very large, then the successive kms are getting spaced very, very closely, and they merge into continuum, real number k. And what used to be a sum over minus infinity m to plus infinity now becomes the density of these little m's. And I can multiply both sides by L, and I can write this as L times minus infinity to infinity delta K over 2 pi. And as I've multiplied both sides of this side, then really this coefficient m times the length will go in something we'll call the Fourier transform continuous function of k. And we end up with Fourier, and I'll drop the word integral, where I have function of x integrated over continuum of wave numbers, and its inverse now looks the way you would want it to look like, because it's also an integral. If you want to compute a function in a Fourier representation space now, that's just an integral from delta x. There is an annoying asymmetry which is inflicted upon us by condensed matter physicists. And depending, who is doing this stuff, they have it or they don't have it. So condensed matter physicists, they claim their physics. You heard about Phil Anderson. They're the real thing. Everybody else is just playing some mathematical nonsense. And they introduce this symmetry. It makes sense, but it's just painful because they've lost the profound symmetry between two operations, and then we'll have to struggle with these 2 pi's all over the place, and you'll make errors in various papers. This thing here, was counting. Remember, it came from m's. So now that can be interpreted as Fourier modes, number of, per spatial unit volume, because we're getting something here, where k, you're in the interval k plus delta k. Field theorists and other people use what you're supposed to use, square root of 2 pi, because then things are symmetric. We saw this in transforms. But anyway, you just have to be aware that there is some nonsense here. You have to also be aware that there is a tradition in this subject. For some reason, physicists have very high opinion on themselves. That's probably because they don't talk to anybody else. And physics convention is now to have a unbalanced Dirac deltas, because now Dirac delta in space, configuration space, in meters, etc., is minus to the infinity delta k, this density of modes, and then the weight of every mode, root of unity, but now there are really lots of them. And what this means is that this is zero every place except at 0, where it's infinite, but it came from being inverse lattice spacing. In other words, this is density. Because you're going from minus to plus infinity, you get formally infinity for 0. That's what it intuitively means to condensed matter physicists. It's a limit of, what happens when you have small lattice spacing. In momentum, this is space, but now in momentum, or wave number, or frequency, or whatever you want to call it, 2 pi is integral from minus to plus infinity. And that means that when you look at 2 pi, and remember, what is this 2 pi? You could have measured everything in the length or in the angle, but obviously in this context, dimensionless angle is a better thing. So 2 pi is really the length of units circle. You're, taking your limit or transforming, making it very, very big so it looks flat to you. And when you look at the origin, then you're computing integral that's just 0. So you're computing integral of dx. And in one dimension, that's line. In d dimension, that's volume. So we call it volume. So that's how physicists tend to think of Dirac delta functions. For them, the space and momentum delta functions are different because they've been made dimensionful. This guy is measured in inches or meters or whatever, and the other one is measured in inverse inches or in whatever momentum. One has 2 pi stuck to it, the other one doesn't. If there was a square root of 2 pi, you would never have to worry about this nonsense.